All right, today we're going to look at the third and fourth objectives in Chapter 5, which is going to look at both the circumcenter and something we call the incenter of a triangle. So let's get right to it. Before we really get into what those two things are, a little bit of background information that we need in terms of terminology that we understand and should kind of all be familiar with. And the first thing is this, is that when three or more lines intersect at a point, okay, those things are called concurrent. Okay, so those lines are concurrent. There you go, nice green lettering for you, concurrent. Okay, and the point at which they intersect, the actual point itself of these lines, is called the point of concurrency. Okay, so if three or more lines intersect at one point, those lines are called concurrent. And the point at which those lines intersect, we call the point of concurrency. All right, so we're going to look at what happens then when we look at the concurrency of perpendicular bisectors. So we're going to look at what happens when we have a triangle and we find the perpendicular bisector of the three different sides of that triangle. And here's what the theorem gives us, is that the perpendicular bisectors of the sides of a triangle are concurrent at a point equidistant from the vertices. Okay, so there's a lot going on here. First thing, we've got this triangle, triangle ABC. And what we've done then is we've found the perpendicular bisectors of each side. And so these are marked in red here. I'm going to kind of highlight over them. So if we took side AB, found its perpendicular bisector, we'd have this line here. Okay, we took side AC, found its perpendicular bisector, we get this line here. We take BC, find its perpendicular bisector, we get this. Okay, and so those three bisectors, those perpendicular bisectors, are all concurrent, right? They intersect at one point, and that point of concurrency is point P. Now, what's interesting about point P is that point P is equidistant from the vertices, right? So the point P here, the distance from P to A, the distance from P to C, and the distance from P to B are all the same. So if we wanted to, we could even make 4 tick marks to show that this distance is equal for all three segments here, PA, PC, and PB, and that's basically what it says in symbols. The perpendicular bisectors here are PX, PY, and PZ. Those are in red. They're all concurrent at point P, and what that gives us is this important information here. Okay, that point is equidistant from all three vertices, same distance. PA, PB, PC all have the same distance or length. Now, what this really leads us to then, if we look at another triangle in which we found that point of concurrency, we found the intersection of the three perpendicular bisectors of the sides, right? We know it's the same distance from P to all three vertices. Well, if we think about this, right, since these are all the same, we could think about these as being the radii of a circle, okay? And what it gives us is what we call the circumcenter of a triangle. And what we can do then is think about this point P as the center of a circle. And if we were to draw a circle with the radius of PA, PC, or PB, right, we get the circle like this. And what's interesting about the circle is that it touches the three vertices of your triangle. It touches A, touches C, touches B. Right? And that's because P is equidistant, same length as the radius here. All right, so since the circumcenter is equidistant from the vertices, we can use that circumcenter, that point P, as the center of a circle that contains each vertex of the triangle. And what we've done then is take this circle and we've circumscribed it about the triangle. Okay, we made basically a circle here that touches all three vertices of the triangle. So the point at which your perpendicular bisectors of the sides intersect, we call the circumcenter of a triangle. Now, based on the type of triangle that we have, that will determine where that circumcenter is located. So there's three different cases here. We can have an acute triangle in which all three angles excuse me, are less than 90. Okay? So we have a nice acute triangle. When that happens, the circumcenter, okay, will always be inside the triangle. Okay, somewhere inside in the interior of that triangle. When you've got a right triangle, okay, in which we have one angle that's exactly 90, right? We've got a right triangle here with our one 90-degree angle, and we find the circumcenter, right, the intersection of the three segment bisectors, perpendicular bisectors, right? That circumcenter is always going to be on the hypotenuse, okay? It'll always be on the hypotenuse of that right triangle. And then if we have an obtuse triangle in which one of these measures here, right, that measure is going to be greater than 90 degrees, so we have one of the angles in the triangle is greater than 90, then your circumcenter will always be located somewhere outside of your triangle. Okay, and again, we can take and draw some circle, the center at that point, and we'd have the circle that would touch all three vertices, okay, and would have a center at the circumcenter. All right, so how can we find the actual circumcenter of a triangle? Well, we're going to look at this in terms of kind of some coordinate geometry. So we're going to take a coordinate plane here, and we're going to create a triangle that has these three vertices, P, O, and S. P is going to be located at the point 0, 6. So we're going to go ahead and plot these. We'll do this in red here. So we go 0, 6, 1, 2, 3, 4, 5, 6. Okay, so there's point P. Point O is at the origin, 0, 0. Easy one to plot. And then point S is located at 4, 0. So we'll go out here to 4, 0, and we'll have S. So we've got this triangle here, and we want to locate its circumcenter. All right, so the first thing we should be looking at here is maybe start to think about, well, where is that circumcenter going to be located? Inside, outside, or is it going to be somewhere on the triangle? Well, if I look at triangle POS, notice that side OS is horizontal, right? It lies right on the x-axis. And side PO is vertical. It's right on the y-axis. So what does that tell us about this triangle? Well, it tells us that we have a right triangle. Okay? So since we have a right triangle, we can go ahead and maybe expect the circumcenter to be on the hypotenuse. Okay, so we're looking at that to probably be on side PS, right? That's our hypotenuse. That's where we should expect to find this circumcenter. All right, so how do we find it? Well, we've got to find the intersection of the perpendicular bisectors of the sides. Now, with other types of triangles, this could be very difficult. However, again, we notice that two of the three sides are both horizontal and vertical. So because side PO is vertical, right, finding its perpendicular bisector should be easy because any line that's perpendicular to a vertical line should be horizontal. So the perpendicular bisector of side PO is going to be horizontal, and we just need to make sure that we bisect it. Well, the distance from O to P is 6, so if we cut that distance in half, it would be 3. Okay, right? This whole distance here is 6. Half of that's going to be 3, so the perpendicular bisector is going to be halfway, and then we can just simply draw in our perpendicular bisector here, right? This should be a right angle, and we've cut that side directly in half. And we can do the same thing with our horizontal side OS. Any side or any line or segment that's perpendicular to a horizontal line is going to be a vertical line. So we know the perpendicular bisector of OS is going to be vertical. And again, we just have to make sure that we bisect it. Since the distance from O to S is 4, right, that's 4, we're just going to go halfway over to 2, and then we can draw in our perpendicular bisector. Okay, and again, we've cut this side in half, we've got a right angle. Okay, now, question becomes, do we have to find the perpendicular bisector of the third side? It would be nice, it'd be handy, but keep in mind, that's going to be difficult because this side here, right, isn't horizontal or vertical, so its perpendicular bisector isn't going to be horizontal or vertical. That's actually going to take a lot of work. The nice thing is, we know that that perpendicular bisector is going to intersect where the other two intersect. So we can already assume this point here, let's put this in a different color, the point of intersection here, which is the coordinate point, oh, what is that, 2, 3? Okay, that's our circumcenter. Okay, all we have to do is find two of the three perpendicular bisectors. Where they intersect should be the circumcenter. And again, we can kind of double check what we thought. We assumed it was going to be on PS, the hypotenuse of the right triangle, and in fact it is. So we know we found the right spot here. And if I'm really good, I don't know that I am, but we'll try, we can even draw this circle. We'll put the center right here, and if I make this out far enough, look at that. You can draw a circle that's got a center at the circumcenter, and if we notice, that circle does intersect all three vertices on our triangle. Pretty cool, huh? All right, so there you go, finding the circumcenter of a triangle. All right, so there's objective 3, finding the circumcenter. Now the other thing we're going to look at is how we can find what we call the incenter. And now we're looking at the concurrency of the angle bisectors, right? Now we want to cut the angles of this triangle in half. So here's our theorem for the concurrency of the angle bisectors. The bisectors of the angles of a triangle are concurrent at a point equidistant from the sides of the triangle. Okay, so again, triangle ABC. In red, we're going to draw in our angle bisectors. We've cut our angles in half, right? Those angles all intersect at point P. And that point P is now equidistant from the three sides. So the distance from P to each of these sides should be the same. And keep in mind, distance from a point to a line always can be found on a segment that is perpendicular to that line. So that's why we have these symbols here showing that, yep, we are perpendicular. So if PA, PB, and PC are all the angle bisectors, they're concurrent at point C, and that tells us that PX, PY, and PZ all have the same length. So what that gives us then, that point of concurrency of an angle bisector, we call the incenter of the triangle. Okay. Now the incenter will always be inside of a triangle. Right? With the circumcenter, it could be inside the triangle, on the triangle, or outside. Incenter will always be on the inside of your triangle. And again, they give us another little diagram of this that shows us that we've got point P, which is the intersection of all our angle bisectors, and that those points are equidistant from the three sides. What this gives us is a circle that we say is inscribed in the triangle. So the circle is inscribed. The circle has a center at point P, the incenter, and then intersects the circle at the points X, Y, and Z, which again give us those three segments that are equidistant from P to the three sides. Okay, so one last quick example and we'll wrap up this portion of chapter 5. So we've got now this nice drawing again of triangle ABC, and we have all these other points here, D, E, F, but we got this point G that's somewhere in the middle of this. And what I want you to see here first, before we even try to answer anything, is that we've got an angle bisector here, right, at C. That's been bisected. Okay, we've got a bisector of angle A here, right? We've cut angle A directly in half. And we've got a bisector of angle B here. We've cut that angle in half. And again, all those three bisectors intersect at point G. So that gives us what? Well, if it's the angle bisector, it tells us that G is the incenter. Okay, meaning G is equidistant from the three sides. And we can see that those distances that are equal are GE, GF, and GD. These three things all have to have the same length. So they tell us that GE is 2x minus 7 and GF is x plus 4. But remember, GE equals GF, which equals GD. Okay, and we want to find the length of GD. Well, we start with this. GE and GF are equal. That means the expression for their measurements, 2x minus 7 and x plus 4, are also equal. So we can solve this equation, get a value for x, plug it in to find either GE or GF, and that then tells us also the length of GD. So if we solve for x here, subtract x from both sides, x minus 7 equals 4. Okay. Add the 7 to both sides, cancel these, and we get a value for x of 11. But again, that only gives us a value for x. Let's use that to find the length of GF. Okay, GF, which was x plus 4. We'll go ahead and plug 11 in for x. We get 11 plus 4, or GF is equal to 15. But remember, since GF, GE, and GD all have the same length, that tells us that GD also has a length of 15. And that's it. That's all of objective 3 and 4, talking about the circumcenter and the incenter of a triangle.